In this session, we're going to look at a specialized version of mod counters. Remember, mod counters are one name for an asynchronous counter, the other names being a ripple counter or a frequency divider. But in this particular case, we're going to look at mod counters that don't use the full count available when you have n flip-flops. So we know from the last video that a mod counter is going to count through a predetermined sequence of values. The one we saw last time was an up counter. It counted from 0 to 15 and then started repeating. The number of the count, or the range of the count, is defined by the number of flip-flops in there. So if we have n flip-flops, we have 2 to the n different possible counts, which gives us a range of 2 to the n minus 1 count values. The nice thing to know is that we always don't have to count through that full range, and that's what we're going to talk about in this session. So here's the mod 16 counter that we talked about in the last session. We have our clock signal, and we have our Q0, which is half the frequency of the clock, our Q1 output, which is half the frequency of Q0, Q2, which is half the frequency of Q1, and Q3, which is half the frequency of Q2. We worked through this and we realized that it counted from 0 up to 15 and then started at 0 again and counted up to 15 again, we can assume. We also know that we did our samples halfway in between the edge that we're detecting, so we were on, based on our diagram, on a falling edge, so we did our sampling at the rising edge of the clock. And that's where we figured out that we had a 0 count, a 1 count, a 2 count, and so on. A lot of times, though, we don't want to count all the way up to 15. For example, there are a lot of times, because we work in a decimal world, we got 10 fingers and 10 toes, we want to have a counter that counts up 10 values. So we want to count 0 through 9, and then we want to restart. For example, a clock, a digital clock, the minutes digits go from 0 to 59, so we need to be able to count for that least significant digit from 0 to 9. So we have what's called a decade counter. It's a specialized version of a mod 16 counter, but it's only going to count from 0 to 9. So in order to design that, we have to work through a specific process. So the first thing we need to do, so the next step is figuring out which bits are high in this binary value that we're going to need to tap into in order to reset our flip-flops. So in other words, when we get to a count of 10, we want to reset our flip-flop so it goes back to 0, starts counting at 0 up through 9. When we get to 10, reset it again and restart that count. So we're never going to let it get to the counts 11, 12, 13, 14, and 15. So what we need to know is for these 2 bits, which outputs do those correspond to? Well, the least significant bit corresponds to Q0, so this one corresponds to Q1. So let's mark that on. This corresponds to Q2. This one's going to correspond to Q3. So what we're going to do is we're going to take the output from Q1 and the output of Q3 and feed those into a NAND gate. So this is a separate NAND gate that we're going to add to our flip-flop circuit. Once we have that, we're going to take that output from that NAND gate and feed it into an input we haven't looked at on the JK flip-flop yet, which is called the asynchronous reset. And that's going to be labeled R with a bar over it, indicating it's active low, or sometimes, depending on the manufacturer, it may be marked as clear or it may be marked as reset. So you would be looking for that. Generally in the diagram for the flip-flop, you're going to see it right down here with J and K being on the side. You're going to see that down at the bottom. There is a matching one at the top, which is a set, and those are used to either set the flip-flop to a high state or clear it to a reset, so that we know the state that we're operating in. Now it's important to recognize that that has a bar over the top, so it's active low, which is why we want a NAND gate here, because when our inputs are active, we're going to get an active low out. So let's take a look at this circuit now. So here we can see the standard configuration for our decade counter or our mod counter. We have the number of required flip-flops. We needed 4. Each of them is wired to toggle, so J and K are both tied high. The clock signal feeds into the first flip-flop, which is Q0. The output of the first one feeds into the second one, giving us Q1. Q1 feeds into the clock of the third one, which gives us Q2. Q2 feeds into the clock of the last one, giving us Q3. You also notice the asynchronous reset we were talking about is shown at the bottom of this device, and that's what we're going to use to reset once we get to that count of 10. Notice also that it's active low, so we need to make sure that whenever we have the 10, the binary value for 10, showing up on our outputs, Q0 through Q3, whenever B1 and B3 go high, so this would be bit 0, this would be bit 1, so we're looking for this one. This would be bit 2, this would be bit 3, so we're also going to be looking to tap into this one. Whenever those go high at the same time, what we're going to do is feed them through a NAND gate, so let's add our NAND gate. We're going to pick up the output from Q3. We're going to pick up the output from Q1. And we're going to take those and we're going to feed them into the reset for each flip-flop. So what that means is when these two inputs go high, in other words, we get to a count of 10, this output will become low, which will reset each of the flip-flops, and a reset, you know, takes it back to 0. So our count will go for a very, very brief period of time. It'll go 0 through 9. Then for faster than we can see, it will go to 10, which, based on the propagation delay of this NAND gate, will immediately reset these devices back to 0. So we'll see a little bit of a blip when it gets to 10, but in terms of our output and the real world, it won't really see that 10. So let's take a look at the waveforms now. So here we can see what the waveforms are going to look like for a decade counter. Not quite complete, we're going to finish that off, but the beginning part is here. So we can see the clock pulse, which feeds into the first flip-flop, which is the one that's going to generate Q0. You can see Q0 counts 0, 1, 0, 1, continuously cycling. Its frequency is half that of the previous. Q1, that cycle takes twice as long, so its frequency is half again. Again, it counts 0, 1, 0, 1 on a regular basis. Q2, half the frequency again, so the cycle takes twice as long to go through that 0, 1 count. And finally, Q3 takes twice as long again to complete a cycle, but in this case we haven't quite completed them. Remember, when we're looking at figuring out what the count is, we're going to sample halfway through the clock pulse. Because we're on a falling edge device, we're going to sample at the rising edges, and we can see the output Q0 through Q3, but when we read them, we have to remember to read Q3 down to Q0. So our output here is going to be 0. When we look here, we can see 0, 0, 0, 1, our output is 1. Next one, 0, 0, 1, 0, our output is 2. 0, 0, 1, 1 gives us an output of 3, or a count of 3. 0, 1, 0, 0 gives us a count of 4. 0, 1, 0, 1 gives us a count of 5. 0, 1, 1, 0, a count of 6. 0, 1, 1, 1 gives us a count of 7. 1, 0, 0, 0 gives us a count of 8. Oops, let's get a pen here. 1, 0, 0, 1 gives us a count of 9. And we can see our full count here for our decade counter. So what we should expect to see now is, because of that reset, that NAND gate that we had that was tapping into Q3 and Q1, waiting for them to both go high at the same time. If we scan through, Q3 didn't go high till over here, and Q1 hasn't been high in either of those. So as we make this next transition, where this one's going to drop, this one is going to rise, this one is going to hold, this one is going to hold as well, and we can see here we have Q3 high at the same time that Q1 is. So we've met our condition here. What happens? This immediately resets. Every flip-flop goes to 0. And what we're going to see is very quickly, this drops back to 0, this is 0, this one is high, it drops back to 0, and by the time we get to that next rising edge on our clock right here, we're going to be sampling and we're going to see a 0 output. So the addition of this nice little circuit allows us to count up to 9 and reset when we get to 10. We can count up to 6 and reset when we get to that. We can count up to and create a mod N counter for whatever we would like. So let's summarize what we know about asynchronous counters. We know they're very simple devices. They're simply JK flip-flops wired to toggle, with the clock feeding into the first one and all the subsequent ones being fed by the clock of the previous one. Very simple. We know they have 3 names. They have a ripple counter, a mod counter, or a frequency divider. We know it's the same configuration, and depending on the application, we might call it something different, but it's basically going to function the same way. We talked briefly about the main disadvantage, and that's we're limited to very low frequencies. Rule of thumb says under 10 megahertz, and that's because of the propagation delay. So we saw that as Q0 was changing, so as Q0 went low, we saw that if it caused a change in Q1, it was a little bit delayed, Q2 was a little bit delayed, Q3 was a little bit delayed from that, and eventually the accumulation of these propagation delays can cause us problems. So if we get up to frequencies above this, we may see that. So very useful device, just make sure we're using them at low frequencies.